Hey everyone! You know when you see an IP address and it's got that weird slash and a number at the end? Ever wondered what that's all about? Well, you're in the right place because today we are cracking that code.
All right, so here's the game plan. First, we'll cover what CIDR notation actually is. Then, we're going to decode that slash number. After that, we'll dive into a couple of real-world examples to make it stick. And finally, we'll talk about why this stuff is so important. Let's do it.
I guarantee you've seen this somewhere. Maybe digging around in your router settings or on some network diagram at work. It looks like a normal IP address, but it's got that little extra thing tacked on the end. And trust me, that little piece is the key to understanding a whole lot more.
So what's the deal with that /28? That right there is the big question. It might look small, but that little number is probably the most crucial piece of information for understanding a network. It's not just random. It's actually an instruction telling us something very specific.
Okay, let's get into it. First up, what even is CIDR notation? Now, the full name is a mouthful. Classless Inter-Domain Routing. Yeah, don't worry about that part. The important thing to know is that it's just a way to talk about a whole group or a block of IP addresses at once, instead of just a single one.
I love this analogy. It's perfect. CIDR isn't just telling you the house number. It's telling you how big the entire neighborhood is. The technical term for this is a subnet mask, but honestly, the CIDR slash number is just a super convenient shorthand for that. It tells you exactly where the network's boundaries are.
Okay, time for the main event. Let's talk about that number after the slash. This is it. This is the key that's going to unlock everything else we need to figure out. Here's the most important thing to get. A standard IP address, we're talking IPv4 here, is made of 32 bits. That's it, 32. The number after the slash, what we call the CIDR prefix, tells us how many of those 32 bits are used to identify the network part. Whatever's left over, well, that's what we can use for our actual devices. And believe it or not, the math is super simple. You just start with 32 always. Then you subtract the slash number. So in our example, 32 minus 28 leaves us with 4. That number, 4, is what we call the host bits. And those 4 bits are our playground for assigning IP addresses to all our stuff, computers, phones, servers, you name it. All right, enough theory. Let's get our hands dirty and actually do this. We're going to take that first example, 192.168.1.0/28, and we're going to break it down completely. We'll figure out everything there is to know about this little network neighborhood. So, like we just figured out, 32 total bits minus the 28 network bits leaves us with 4 host bits. That little number 4 is the magic number here. Everything about the size of this network, how many gadgets we can actually connect, it all comes down to those 4 bits. Okay, so that leads to the next puzzle, right? If you've got 4 bits to play with, how many different addresses can you possibly create? This is where a little bit of binary math comes in, but don't worry, it's easy. The answer is 2 to the power of our host bits. So 2 to the power of 4 is 16. That means we have a total of 16 IP addresses in this block. But, and this is a really important but, we can't actually use all of them. Yeah, there's this rule in networking, it's pretty much universal. You always lose 2 addresses. Why? Well, they have special jobs. The very first address in the block is the network address itself. It's like the name of the street, not a house on it. And the very last address is the broadcast address. That's used to shout a message to every single device on that network all at once. So, simple math again. We take our total of 16, subtract those 2 reserved ones, and we're left with our final answer. For a /28 network, you can connect 14 usable devices. That's it. And here's the whole summary, all laid out nice and neat. 14 usable hosts, the network address is .0, the broadcast is .15, and that means the actual addresses you can assign to a device run from .1 through .14. See? Not so scary. We totally decoded it. Okay, so you've got /28 down. You're a pro. Now, what happens if we just change that number by 1? Go from a /28 to a /27. Well, that means we get 1 extra host bit, right? We go from 4 to 5. It sounds like a tiny change, but you're about to see what a massive difference just 1 single bit can make. Let's try another one. This time we'll use a totally different IP range, but with that /27 prefix. Don't worry, the process is exactly the same. You're probably already doing the math in your head, right? We start with our 32 total bits. We subtract the new prefix, 27, and that leaves us with 5 host bits. Easy.
So what's 2 to the power of 5? It's 32. Check that out. By just changing that one little number in the prefix, we literally doubled the size of our network. We went from 16 total addresses to 32. That is the power of binary, my friends.
And of course, we got to subtract our 2 reserved addresses. So 32 minus 2 gives us 30. A /27 network gives you 30 usable IPs for all your devices. And here's the final breakdown for the /27. 30 usable hosts. The network starts at .0, the broadcast is all the way at .31, and everything in between is fair game. See? Same exact logic, just a bigger network. Okay, so we get the math. That's cool. But why? Why does any of this matter? Why do network engineers go through all this trouble of carving up networks, which is a process we call subnetting? What's the big deal? Well, it really comes down to 2 big things, being efficient and being secure. Think about it. Instead of having one gigantic, messy network for everyone, you can create these perfect, custom-sized little networks, or subnets. So a small department that only needs 14 addresses gets a network with exactly 14 addresses. No waste. It also builds walls between parts of your network. You can keep the accounting department's traffic totally separate from the public guest Wi-Fi, which is huge for security. And honestly, it just makes things faster. Remember that broadcast message? In a smaller network, it doesn't have to scream across a massive, noisy digital room. And there you have it. That / number isn't so mysterious after all, is it? It's actually a super powerful tool for building smart, secure, and efficient networks. Now that you've cracked this code, the real question is, what other network mysteries are you going to solve next? Thanks for joining me.